Hello, everyone. Today we are going to talk about two more tests, which are called ratio and root tests. Well, let me remind you first, um, like how geometric sequence looks and like what special relations are between the terms of geometric series. Well, you probably remember something like this. Geometric series is going to look like E plus AR plus AR square, AR cube, and so on, right? We know that this series is convergent if absolute value of R is less than 1. We know that in all other cases it's divergent, right? Well, if somebody gives you geometric series, how would you find R? The simplest way to do this is to compare two terms which are next to each other. For example, this term and this term. This is term, let's say, number 2, and this is term number 3. You see that we get term number 3 by multiplying term number 2 by a ratio. I'm going to write it down. So term number 3 equals term number 2 by a ratio. I'm going to put in parentheses more general expression. Term n plus 1 equals term n multiplied by a ratio, right? From where we can calculate ratio by dividing A3 over A2, and that's going to give us a ratio. In general case, we calculate ratio by dividing AN plus 1, the next term, over the previous term, n. Well, so we know that if ratio is less than 1, the series is convergent. Now, imagine that we have a series which is looking similar to geometric series. And I'm going to use as an example series which we already had in class, but we used actually a limit comparison test for it. My first example is going to be, let's consider series which looks like 1 over 2n plus 1 n from 1 to infinity. From not even from limit, just from comparison test, we know that this series is less than the series 1 over 2n and goes from 1 to infinity. This one is G series. Sorry, okay. This is G series, and the ratio of this series, oh, it's kind of slow. G series. And R here is going to be what? I'm going to just calculate it using my formula, which I just developed. It's term n plus 1, which is 2 n plus 1 over 1, 2 to the power of n, right? And if I simplify this, I'm going to get 1 over 2n plus 1 multiplied, if I flip this over, by 2 to the power of n over 1, which is going to give me 1 over 2, which is, of course, going to give me convergent series because R here is equal to 1 over 2, less than 1, convergent, right? So we apply over here comparison test. Comparison test. More precisely, direct comparison. Because we have just inequality sign, right? We know by direct comparison that my series is convergent because it's less than convergent series. Terms are positive, everything is fine, right? Now, guys, let's look how terms of this new series, not new series, but my kind of unknown series, are behaving at infinity, how they are behaving. So what I'm going to do, guys, I'm going to find the ratio between term n plus 1 and term n for this series. This is not G series. So generally speaking, I should not find that ratio. I'm just doing it just to check like how the ratio behaves. I already know that the series is convergent. Everything is perfect with this. Just because I want to use this as an example, I'm going to calculate this ratio. So I'm going to write down. So it's 1 over 2 to the power of n plus 1 plus 1 and divided over 1, 2 to the power of n plus 1. Again, we are going to flip it over. We're going to get 2 to the power of n, and here 2 to the power of n plus 1 plus 1. I'm going to divide both numerator and denominator by 2 to the power of n, and we'll get 1 plus 1 over 2 to the power of n here. And sorry, I was trying to draw 1, but that's going to be 2, right? If we divide by 2 to the power of n, it's going to be like 2. So guys, that's what we have, right? If n goes to infinity, this term will go to 0, and this term will go to 0. And my ratio is going to be equal to 1 over 2. It's going to be exactly as a ratio of the series I was doing comparison. Why? Well, because they're so close to each other. There are only little difference at the very denominator, and at the end of the series, somewhere at infinity. This difference is not going to make any real difference because it's number 1 is going to be infinitely smaller in comparison to 2 to the power of n. Just consider n equals 100 or 1 million. So this allows us to think that maybe if my series is looking like geometric series, I don't need to do like limit comparison test or direct comparison test, but I can just see how the ratio between terms behave. If ratio is equal to a constant number like 1 over 2, and this constant number is by absolute value less than 1, I can say, well, my series is going to look like geometric at infinity with ratio equals 1 over 2. It's going to behave like geometric, which means that it's going to be convergent just because the ratio is less than 1. And this way, we are going to develop so-called ratio test. Let me write out ratio test. Ratio test. So ratio test is going to have 3 parts. Part number 1, if limit between terms n plus 1 over term n goes to infinity, is equal to L and less than 1, then series an is absolutely convergent. And I'm going to and from this is going to say that it is just convergent. Remember that absolute convergence is strongest type of convergence. So if absolutely convergent, then it's normal convergent, right? Number 2, if limit an plus 1 over n goes to infinity equals L, but it's greater than 1, then series an is divergent. Well, means that it looks like geometric series with ratio greater than 1, like 3, for example. If it's going to look like 3, 9, 27, of course, this series, if you sum up the terms, each term will go to infinity. And if you sum up those terms, they're definitely going to give you infinity sum. Okay? And the case number 3, guys, you see that there are 2 cases. Limit is less than 1, limit is greater than 1. And of course, there is going to be a case of limit is equal to 1, right? If limit an plus 1 over an, sorry, my subterm is supposed to look like subterm, not just addition, is equal to 1, unfortunately, the test is going to be inconclusive. Inconclusive means that really the test is too rough to investigate that series. The series is more subtle to use this test on it. And almost in all cases, it's going to mean that the series is not looking like geometric series. So ratio test works well on the series looking like, I'm sorry, I'm going to make it a little bit smaller, geometric. So not all our series are looking like the geometric, right? So some of them are not. So ratio test is going to work on those which are looking like geometric. In comparison to comparison test, let's compare ratio test and comparison test. Guys, remember that for comparison test, you will need two series, AN and BN, two different series. One is supposed to be either convergent or divergent, and you make a comparison with unknown series. For ratio test, you need just the same series. So here you compare terms of the same series. Here you compare terms of two different series. It's still going to be a limit, but two different series, the same series. Okay. And let's consider example of how we use this nice ratio test. Ratio test is going to become one of your favorite tests. Why? Because lots of series in our life are going to look like geometric. So my example number 2. Let's consider series, which is going to look like -1 to the power of n to the power of 4 divided over 5 to the power of n goes from 1 to infinity. Let's build a limit. How do I know that I can use ratio test? Looks like geometric series. 5 to the power of n. I'm going to circle it like G series. Again, there are more stuff here, more than normally G series is going to have, but it looks like. So why don't we try geometric series? So n goes to infinity, absolute value an plus 1 divided over an. So we'll need to carefully increase n by 1 unit in our term. And guys, because we are taking absolute value here, I'm going to drop -1. We're taking absolute value, so I'm going to drop -1 because absolute value of -1 is going to be like just 1. The rest of the series does not have any changing sign, so I'm just going to drop absolute value here because it's not going to be like, not going to work against the numbers. So I'm going to use my n plus 1 term, n plus 1 to the power of 4, 5 to the power of n plus 1, and here in denominator, n to the power of 4, 5 to the power of n goes to infinity. Again, I don't need here absolute value, but if you wish, you can write it down. Here, everything is positive. I'm going to now kind of simplify it, and I'm going to deal with similar terms or like factors like together. For example, n plus 1 to the power of 4, I'm going to divide by n to the power of 4. And 5s are going to come by themselves also separately as a separate fraction. You will see why it's going to be fixed. Well, I'm going to keep limit I'm going to, because the power of n is the same here and here, I'm going to put it in one parenthesis, n plus 1 over n to the power of 4. 5 to the power of n is going to cancel, and I'm going to just have 1 over 5 here, and n will go to infinity. Now, I'm going to divide by n, numerator and denominator by n in my fraction. I'm going to get 1 over n, and here 1 to the power of 4, n goes to infinity, and multiplied by 1 over 5. Well, you probably see that the limit, this one will go to 0, and the limit is going to be just 1 over 5. 1 over 5 is less than 1, so ratio of our geometric series is 1 over 5, like we suspected actually. Less than 1, up, convergent, absolutely. Why do we say absolutely? Because we actually took absolute values of the terms. We kind of first strip our series of all minuses. Random minuses, alternating minuses, we don't care. And then apply the test to like absolute values of the series. And if it's convergent, absolutely, we're going to tell that original series is convergent because it's convergent absolutely. Absolutely is kind of heavier convergence. So the series by itself is convergent too. Not only absolute values are convergent, but the series with all the minuses is going to be convergent. Okay. Now, guys, let's consider two more examples. Example number 3. I'm going to consider harmonic series -1 to the power of n over n goes from 1 to infinity. This is alternating harmonic. We know about this series that this series is convergent, right? Convergent. We know already. We know. Also, we can see does not look like, sorry, mine doesn't look like G series. If series doesn't look like G series, most likely ratio test is not going to work on it. But let's see how it's going to look. Well, same minus is going to disappear, and we are going to have 1 over n plus 1. Here, it's not a power. N plus 1 over 1 over n goes to infinity. Again, I'm not writing down absolute value because already kind of, let me put it what I'm calculating. An plus 1 over n goes to infinity. I just dropped the minus. So what I'm going to have, limit of n over n plus 1, n goes to infinity. Guys, we already had the same limit over here, just like upside down, but if it was 1, upside down is going to be 1 again. You can divide numerator and denominator by n. You're going to figure out it equals to 1. So ratio test is inconclusive. But we do know that the series is convergent by alternating series test. By alternating series test. This test is inconclusive, but different test is going to give us the answer. You see. Okay, example number 4. Now let's take normal harmonic. Normal harmonic, remember, it's divergent, right? Harmonic series. What harmonic series? Divergent. What test did we use to show it divergent? I'm going to put like by integral test. Okay, let's see how ratio test is going to work on this one. Again, this one does not look like geometric series. Same. Well, I don't want to copy it over here, but it's the same. Doesn't look like geometric series. Let's see how this ratio test is going to work. An plus 1 over n goes to infinity. That's going to be the limit. 1 over n plus 1, 1 over n goes to infinity, and we are going to get again the very same limit, n over n plus 1, and you probably already see that the limit is equal to 1, and the ratio test is inconclusive again. Well, you see, I wanted to illustrate by these two examples, example 3 and example 4, that inconclusive does not mean that the series is divergent, means that the test is not good. But different test is going to tell that this one is divergent and, sorry, example number 3 is convergent. So that's just like we already know this from a different testing. Our ratio test is inconclusive. Most likely, guys, if you get a ratio test inconclusive, means that you were not supposed to use the ratio test on that series. Just series does not look like geometric series. Okay, so maybe we need to consider maybe more examples. Let's do one more example before we move to the root test. Okay, let me change my color again. I don't know. I'm going to consider example with factorial because I know that you guys are not very good with factorials. So why don't we consider example with factorial? Minus 3 to the power of n over n factorial. N goes from 1 to infinity. N factorial, it's a product of all numbers from n minus 1 to n minus 2, and until you have like 2 and 1 at the very end. Product of all numbers from 1 to n, right? So, yeah, this series maybe is not looking like geometric, but factorials are going to count toward geometric too, because they are very rapidly growing functions. And 3 looks like geometric, you know. So why don't we try this ratio test limit? N goes to infinity. I'm going to label an plus 1 an. And then I'm going to kind of carefully increase amount of n's in my series n plus 1 here, right? N plus 1 factorial denominator minus 3 to the power of n and n factorial. Looks a little bit crazy, but what you will want to do for get rid of the minus because we have absolute value and then combine similar terms together, similar factors together, let's say. I'm combining 3 together and I'm going to combine factorials together because it's easier to work with similar expressions or simplify them. 3 to the power of n cancels, and we are going to have just 3, right? What is going to happen to factorial, guys? On the top, we do have n factorial. What is n plus 1 factorial? It's n plus 1 multiplied by n minus 1, and so on. So actually, n plus 1 factorial is n plus 1 by n factorial, because you're just increasing n by 1 unit. You can cancel n factorial from here and n factorial from here. And your limit is going to be 3, which comes from the 3 part, right? And n plus 1, which is remainder from factorial. When n goes to infinity, obviously will be equal to 0. And usually people think, oh, 0, we don't know what to do with it when our test maybe is not working. Yeah, guys, remember, comparison test is not going to work when it's 0. Limit comparison test. But our test is working because 0 is less than 1, absolutely convergent. You see? So that's how we deal with factorials. And sometimes we are going to mix up factorials and others. Now, guys, we are going to move to one more test, which is similar to ratio test, but applied in slightly different cases. Guys, to verify the root test, I want to consider very special G-series. I'm going to consider G-series where A equals 1. So it's like 1 plus R squared, R cubed, and so on. Guys, how else we can calculate actually the ratio if you don't want to find the ratio between two terms? We can actually consider term number 3, for example, and extract the cubic root of R cubed. And that's still going to give you the ratio, correct? So if you consider term number n and extract nth root, that's going to give you the ratio. And all conditions for this ratio are going to be same. So basically, root test, it's a same ratio test, but when you don't want to deal with two terms, but you want to deal just with one term. And you can take that one term and extract nth root out of that term. I'm going to kind of write down the conditions of the ratio test. But guys, I don't want to write down 3 different conditions. I'm going to write down one limit, and I'm going to do 3 different arrows from it. So we take the term, strip it out of the sign, all minuses and pluses which are present over there, and extract nth root out of it. Okay, so like we did over here. So there are 3 possibilities. I'm going to use different arrows. I don't want to copy like all expressions. So first, this limit can be less than 1 and then convergent absolutely. Can be greater than 1, divergent. And it can be exactly equal to 1, inconclusive. Guys, I personally almost never use the root test. Only if I see very, very obvious expression from which I know, okay, if I extract nth root, it's kind of going to be easy to find the limit. I usually never use it. So I'm going to consider example, which is a little bit complicated, but the root test on it is going to be like faster than the ratio test. Usually, guys, all tests, all series which you can solve with root test, you can also solve with ratio test, just maybe a little bit longer. Let's consider example. And what was 5? Example number 6. Example number 6. Well, I'm going to consider like long, complicated series, obviously connected to geometric series because it's going to have lots of nth powers. So kind of complicated series, 10 to the power of n, 4 to the power of 2n plus 1. Again, I'm going to use the root test, and you will see that root test sometimes is a little bit longer than ratio test. So this series does not have any variation of a sign in terms. So I'm going to write down root test. Limit n approaches infinity and root out of 10 to the power of n plus 1, or 2n plus 1. Guys, here you can take absolute value, but it's not necessary just because everything is positive. Guys, we remember how we take nth root. It's actually raising to the power 1 over n. I'm going to write down nth root. It's the same as the power of 1 over n, right? So I'm going to raise all my factors into that power. So 10 to the power of n to the power of 1 over n. One more thing, if you have power in the power, you just multiply them, just in case you forgot. Okay? In denominator, 1 to the power of 1 over n, and 4 2n plus 1 multiplied over 1 over n. Oh, lots of several story numbers. Okay, for 10, we are going to have this and this canceled, so we are going to just have 10, right? For this one, nothing is going to cancel, we're just going to copy it. And for this one, if you simplify it, you are going to have 4 to the power of, like, if you divide by n over here, it's 2 and 1 over n. Limit as n approaches infinity. Guys, it's obvious that this term will go to 0, and we are going to have like 10 over 4 to the power of 216, and limit, like something what depends on n is going to be 1 over n plus 1 to the power of 1 over n. So we'll need to figure out what is this limit. And here, guys, we are going to use our favorite L'Hopital's rule. So I'm going to calculate this limit separately. Sorry, I'm going to make everything smaller so you can see everything at once. So let me round it up, and I'm going to calculate it separately. I'm going to consider a limit of, maybe I'll just consider denominator. You know, guys, or let's do it like this. N plus 1 to the power of negative 1 over n. I brought it in numerator. I don't want to deal with denominator right now. So guys, if I move it to x, because I cannot kind of use L'Hopital's rule on n, right? I can use L'Hopital's rule on n. Must use x. Okay, limit as x approaches infinity, x plus 1, or maybe 1 plus x, and here negative 1 over x. Guys, we probably have seen this limit. Do you remember it? No? Remember a long time ago, I'm planning to use L'Hopital's rule here, but long time ago, somewhere in chapter 6, we had this limit just without minus sign, and it was giving us number e. Remember, I was talking about e as a limit, and it was 1 plus x, 1 over x, just without minus. So actually, guys, I expect the final answer to be equal to 1 over e. But let's use L'Hopital's rule. If I promised already L'Hopital's rule, why don't? So L'Hopital's rule is going to be here what? We are going to have over here infinity. So actually I'm not writing down 1 over e, because here x does not go to 0. It's supposed to go to 0 to give me e. I was wrong. Here x goes to infinity. I'm going to just use L'Hopital's rule. We have infinity to the power of 0, so say infinity, yeah, to the power of 0, which is always like a questionable thing, right? So usually when we deal with powers like this, we are going to take a ln of our expression. A ln of 1 plus x to the power of negative 1 over x is going to give us negative 1 over x by a ln 1 plus x. It's already a fraction, so I'm going to write down a ln of 1 plus x for x was minus. So if I use, well, when x goes to infinity, this goes to infinity, this goes to infinity, so everything is fine. We can use L'Hopital's rule. And I'm going to differentiate ln. It's going to give me 1 over 1 plus x, right? If I differentiate this expression, I'm just going to get 1. And differentiating x is just going to give me 1. Okay, good. So now, because I'll need a limit as x approaches infinity, I'm going to have just 1 over infinity, which is going to give me 0. To go back to my result, I'll need to return back from ln and put e to the power of 0. That's going to be my limit, and my limit is 1. So I'm going to use this fact over here, and my total limit is going to be 10 over 16 by 1. 10 over 16 is obviously less than 1, right? Because 10 is less than 16. So series is convergent. Absolutely. Well, again, not always you will need to use L'Hopital's rule when you use root test. But again, you don't use root test without a reason. If you see that it's easy to extract a root and then find the limit, then use it. If you see that it's not easy, maybe just use a standard threshold test. It's going to be faster. Okay? And that's all about ratio and root test. You will just need to do some exercises, practice a little bit. Just remember one thing about ratio and root test. They are applied on the same series, in the series itself. In comparison to limit comparison, indirect limit comparison, indirect comparison, when we compare two different series, this thing is applied to one series. And conditions are different, right? There, we need just a number. Number can be any number, 5, 10, 15, we care that it's not 0 and not infinity. Here, we actually care that it's less than 1 to make it convergent. Okay, that's all for today, and see you next lecture.